Hello everyone, and welcome back to another remote sensing lecture video. And in this video, I want to sort of wrap up our discussion on spectral response curves and spectral profiles by talking about what is probably their most useful application in terms of remote sensing. So we've already talked about how we can interpret a spectral response curve for a particular object to sort of maybe pick out what wavelengths we should be focused on. But in terms of remote sensing, what is arguably almost a more useful application for spectral response curves is the idea of identifying what are called discriminating features. And we'll say discriminating features. Discriminating features. Right, and discriminating features are basically just bands or wavelengths or in later videos, right? Not now. In future weeks, in future videos, we'll talk about things called indices. Right? Basically, they're anything that we can calculate in remote sensing that help separate objects. And spectral profiles really are a great tool in helping identify these discriminating features. And so what I want to do in this video is I want to go through a real example. Right? All of this data was pulled directly from an image in ArcGIS Pro. I want to go through a real example of how we would use spectral profiles to determine the most useful discriminating features to separate out three different objects. Now, full disclosure, these are just three spectral profiles. You'd probably want to do a lot more to get a good average, to get a good sense of that you're making the right choice here. But this is going to give us just a good sort of example of how I would approach this, and also how we can connect what we see in a spectral profile to what we might expect to see in an image. So first of all, we have the spectral profile. You're going to notice that this is a spectral profile because we have band numbers along the bottom, and we have this weird 0 to 3,500 value on the y-axis. And that's because we're now dealing with actual spectral profiles that are coming out of software. So the first thing that you would want to do if you were given something like this would be to look at the x-axis and say, well, what do these band numbers represent? So you'd have to do a little bit of legwork here. You'd have to figure out what sensor you're using. You'd have to go to whatever database you have access to figure out what wavelengths these bands correspond to. So I've saved us a little bit of time, and I've actually went ahead and I've grabbed the Landsat 8, which is that sensor. I've grabbed its wavelength specificities. And so we have the first 7 bands here, and you'll see that we have the wavelength regions, right? So this is in the blue, this is also in the blue, this is in the green, red, NIR, and then 2 shortwave infrared. Now, we don't have any of these included. They're in a different data set that we're not going to worry about. But anyway, so we can go back here, and we can say, we can label these. We have blue 1, blue 2, green, red, NIR, SWIR 1, and SWIR 2. Okay, so now we sort of know what wavelength regions we're looking at. So how do we use these spectral profiles to find these discriminating features? Well, what you're going to want to do is you're going to want to look, what you're going to want to do is you're going to want to look at the differences in the distances between the lines at a given band, right? And what I want to do is I want to go through these distances and how they would relate to the grayscale values of each band in the image. So we're going to scroll down here. And what I've done here is this down here. This is the same spectral set of spectral profiles we were just looking at. Right here, this is a true color high resolution image so that we kind of know what sort of feature we're looking at. So blue was taken from what appears to be some sort of a river. Green was taken from some woody vegetation, and orange was taken from a patch of bare soil. Right, and so if you go back and watch some of the previous videos in this section, you'll see that these shapes actually correspond pretty closely to what you would expect to see for those sorts of features, right? Water is really flat. Soil has a tendency to increase through the visible spectrum, and vegetation has low in the blue, a little bit of a green peak, low in the red, and then jump up in the NIR. So we're consistent with what we would expect, right? But how do we use this information to figure out those discriminating features, right? How do we decide, well, what band or bands are most useful to us if our goal was to separate out water from vegetation from bare soil? Right, we're going to talk about the idea of classification later in a different set of videos, but we're really sort of getting at the sort of beginnings of that concept right now with what bands am I going to want to use if I were going to try to pull these different things out of the image. So let's go ahead and start off by looking at band 1. Right? So band 1, right, to sort of box it off, right? This is band 1. Band 1 also corresponds to this top image right here. And you can see that I've clipped out, so this is the actual image that those spectral responses or spectral profiles came from, right? And so what I want to do, actually, let me scroll up just a little bit, see if we can look at the larger size one. Okay, we can, perfect. So what I want to do here is I want to sort of compare in broad terms, right, the relative distance between here and between here and here, right? These two are close together. So you would likely expect them to have very similar gray values in this image here, right? Because they're close together, their pixel values are close together. It means that in the image, right, they're going to look similar in tone. So this is kind of a darker gray, and that's kind of a darker gray. Now compare the distance between these two relative to this one up here, right? The difference between the green and the blue relative to the orange. And you'll look and see, well, this is a relatively larger distance. So as you would expect, right, these are both similarly dark gray, but this is a relatively bright white. Hopefully that makes sense, right? Hopefully that connection between the relative distances and their differences in tone is helpful. Okay. Let's look at another example. Let's look at band 5 to prove to you that it's not just in one direction. So let's look at band 5. All right. So band 5 is this band. So this image right here, this is band 5. So now in this case, right, we have almost the opposite occurring, right? Now in this case, right, the relative distance between green and yellow is low, relatively low, compared to the distance between green and yellow and blue. So in this case, right, we would expect green and yellow to be similar in tone, and they would be brighter than the water. And that's exactly what we see here, right? Green and yellow are very similar in tone compared to blue here, which is almost black because it has very low, a very low pixel value. Hopefully that makes sense. So let's go ahead and look at one more example. Let's look at band 7. So band 7, right, you'll see that, there's this distance here and this distance here, right? It's still not, this isn't in the middle by any means, but this distance is a lot greater, right, than it was in any of these others. So what this is maximizing the difference, right, between these, right? This maximizes, right, let's use a different color. How about orange, right? This maximizes the difference between the objects. And so if you look at this, you might say, okay, well, we would expect, blue and green to be different or far more different than, say, in band 1. And we would expect them to both be more different than here, than between green and yellow. And that's exactly what we see here. Actually, I should specify, right? This right here, this is band 7. Right? That's exactly what we see here, right? This band, right? This is where the differences between each of the objects is the highest, and you can see in the image that holds true too, right? The difference in tones is the most noticeable, right? You can most noticeably differentiate between the water and the forest and the sand. And if we go back up through sort of and have all three of these together, if I can do this just right, maybe I can't. Right, but you can see here, right, if we were to take band 1 as our only sources of information, you can easily distinguish the orange, but you'd have a hard time telling apart the water and the forest. If we took band 5, right, you'd have an easy time differentiating water from everything else, but you'd have a very hard time differentiating the soil from the forest. But if we take band 7, right, you have a pretty easy time, relatively speaking, differentiating between the soil and the forest and the water. And that's what it means when we try to pick the band that has the greatest difference between all of the options. Okay? So I want to wrap this up by sort of codifying or solidifying, right, that idea. That we can use spectral profiles to find the bands with the greatest difference between all the objects. Right. And I underlined all here because ideally, right, in a perfect world, you're going to want to pick the band that has the most difference between all of them, right? You wouldn't want to pick this one because forest and water are really close together. You wouldn't want to pick this one because sand and forest are really close together. You would want to pick this one because they're all kind of different, right? Hopefully that makes sense. I know there was a lot. I'd encourage you to pause, go back, rewatch the parts you're confused about. And as always, please reach out. Thank you.